All right, so let's try this one here. We've got the looking at a hydroelectric plant, and we're actually going to be looking at the specific energy, not the energy density, but the specific energy of this, which is, you know, how many joules per kilogram do you get out of the water that's used in this hydroelectric plant if all of that water energy is turned into rotational energy, and the fall is 80 meters. And so, yeah, you know, you're gonna have to think through this a little bit in terms of, you know, specific energies. You know, how many joules per kilogram do you get? So go ahead and draw it out and think through this and see if you can get it. And when you're ready to check, you can hit play to continue. Okay, so what kind of energy does it have up there? Well, it's got potential, right? So all that potential energy turns into mechanical energy, which turns the generator and produces electricity. And so for 1 kilogram of water up at a height of 80 meters, it has 784 joules, which can be converted. So for every kilogram of water, that's how many joules, and that's the, and again, not energy density, which would be joule per meters cubed, but joule per kilogram, which is energy, specific energy. Go ahead and calculate also how many megajoules per kilogram, because sometimes we'll do that. And so yeah, go ahead and pause the clip and do that, and when you're ready to check, you can hit play to continue. All right, so it should be 7.84 times 10 to the negative fourth megajoules per kilogram, which is a whole lot less than those fossil fuels that we've looked at. With the fossil fuels, you know, the energy density is much higher and than this one. So with wind turbines, it's important to consider, you know, advantages, disadvantages. Obviously, an advantage is it's renewable. You know, you just got the wind blowing through, and, you know, you can harness that energy, and it's clean. There's no, you know, side effects or in terms of, you know, greenhouse gases being released or anything like that. So it's good that way, but there are many disadvantages for sure. You know, you're not getting very high efficiency, although they are getting better with these. The initial cost is very expensive. It's not cheap to make the wind turbines. You're also very dependent on the location. You know, are you getting a lot of wind or not? And but again, the cost is a major detriment here. All right, so with wind power, we're harnessing the energy, kinetic energy, right? And so 1/2 mv squared. And so, you know, how are we going to evaluate that based on, you know, the air going through the turbine? So if you think about it, you know, you got your turbine. It's a different color here. Here's your wind turbine, right? And you have a certain area that's going to be going through. Now, this column of air that has a certain area, we'll just draw that here, is pi r squared, right? Now, the width of this, you know, like how thick this column of air is. Let's try to draw how thick the column of air is here that passes through is dependent on how fast it is. It's V, right? How many meters per second goes through. So in other words, what you're finding out is, okay, I know the area, I know how wide it is based on V, and we need to know the density. And when we multiply that in, we get the mass of that column of air here, and that passes through per second. It's given per second. So what ends up happening is if we place that in for mass, we end up getting 1/2 rho AV cubed, and our units will work out here to be a joule per second. And so V is the speed of the air going through, A is the area of the wind turbine, and then rho is the density of the air. And so, yeah, we get how many joules per second. So let's go ahead and try this one here. We have a wind turbine. The length of the blade's 43 meters, and the speed of the air coming through is 22 meters per second. And it's only 25% efficient. We want to figure out, you know, the energy produced in 15 minutes. So, yeah, go ahead and pause the clip and give this a try. And when you're ready to check, you can hit play to continue. Okay. So here is our value for if it was 100% efficient, and it's only 25% efficient. So this is how many joules per second we get. Therefore, you know, if we have 900 seconds, we can get the total power And well, get the total energy, 7.65 times 10 to the 9th joules. Now for this one, we have a turbine blade of 50 meters, and we have the density of the air. The speed of the air coming through is 8 meters per second. And we want to find the effective power production if the wind is 35, or if we're getting 35% of effective power, how much energy is produced in 35 minutes. And so we know that's only 35% efficient. So yeah, go ahead and pause the clip and give that a try, and then we'll work through that. All right, so what we should have then is pi r squared. We get the area. So we know the area, we know the speed going through, we know the density of the air. And so this is the power output. Now, we're only getting 35% of that, so we multiply by 0.35. And so this is the effective power output. And that looks like, what, 844,460 joules per second, or watts. And so we've got the effective power output, and therefore, over 35 minutes, which we know power is energy over time. It's 2100 seconds. You take 35 times 60 to get the time. This is the effective power. Now, the second part of this that we're going to address is, what is the energy density, or the specific energy of the air going through the turbine? In other words, how many joules per kilogram? And really, you could use specific energy would be better to use, because joules per kilogram is specific energy. And now I have the hint here, the mass per second of air going through the wind turbine is rho v pi r squared. So in other words, if you look at that column of air here, you've got pi r squared, which is this area, and then v is meters per second. So meters per second. In a second, how many meters comes by? And if you multiply, the area times the width here, you get volume. So really, you're multiplying volume by density to get mass. And and that should do that there. So go ahead and pause the clip and give this a try. And when you're ready to check, you can hit play to continue. Okay. So for that, we get this is 75,398.224 kilograms every second. So over 2100 seconds, this is the total amount of mass. So if you take the energy divided by the mass, we get 11.2 joules for every kilogram that passes through. And that's the specific energy.